Hello, my name is Ian Aguilar, and this is my ME210 video assignment 3. And this is the rolling rock problem and the conservation of energy between bodies. And the problem is that Ian is pushing a rock uphill at 15 degrees above the horizontal at 2 feet per minute. As he's pushing the rock, he slips and the rock rolls down. Ian made it 12 feet up the hill before it rolled. How fast did it roll when it reached the bottom? Some of the givens and assumes that I found was that the initial height is 12 feet. The angle of elevation is 15 degrees. The height 2 is 0 feet. The velocity 2 is are unknown. Velocity 1 is equal to 2 feet per minute. We know that the rock is going to roll. That's going to be important for later. We assume that the gravity is equal to 32 feet per second squared. We're going to neglect air resistance, neglect friction between road and rock, and assume rock is circular. So in my diagram, we have that the initial height is 12 feet. I kind of switched the values, but that's my fault. Sorry. Initial height is 12 feet. The second height of the rock is 0. The velocity going upwards is v1 at an angle of 15 degrees. And then for my once it's coming down the hill, again, the v2 is going to the left at a height of 0. As well as our free body diagram, the x and y axis is just a very standard one. We can see that the weight is pulling it down and the normal force is reacting while velocity is going up to the right. And then once it's in down the hill, again, weight pulling it down, and normal force pulling it up, and velocity going left. And here are the equations to solve the problem. So we know that T1 plus V1 is equal to T2 plus V2, which is the conservation of energy equation, which then further goes into as kinetic energy plus potential energy initially, which is equal to kinetic energy plus potential energy minus weight after the rock has been rolled down the hill. This further goes into as 1/2 mv squared, or 1/2 times mass times velocity squared initial, plus mass times gravity times height initially, equals 1/2 mv squared after the rock's rolled down, plus 1/2 of the inertia times the angular velocity. This further goes into as 2/5 times mass times radius squared. That's just the inertia equation for a rolling ball. Then it's multiplied by the angular velocity, which is equal to velocity 2 over radius squared. The reason why is because the rock is rolling, which is rotational kinetic energy. Regular velocity would not work for this rock. And some key concepts for this problem is that, one, plugging in for conservation of energy, so knowing the equations for those. Conversions from feet per minute to feet per second, because we know the velocity 1 is from feet per minute. Knowing the inertia for the rolling ball, just that's some background context. And then knowing the difference between velocity and angular velocity, since those are two different velocities. And thank you for watching. I really appreciate it.